So now that we, in the previous video, went through these basic identities that are going to be our tools in the toolbox, so to speak, now we have to put them to use. And so, again, if you've looked forward in the notes, you see these statements that we're asked to verify. And so we've got some guidelines that we need to make sure that we lay out before we get to work. And so first of all, our rule is going to be that we're going to be trying to turn the left-hand side of a statement into the right-hand side. So if we look forward here, that means that we're allowed to make changes over here on the left-hand side of the problem by making substitutions or doing cross-canceling or whatever it is that we end up doing. But the right-hand side is untouchable. We're trying to turn the left-hand side into the right-hand side. The way we're going to do that is by making substitutions. So using some of our identities, if we see a cosecant someplace, we can replace that with a 1 over sine. Or if we see a cosecant in the denominator, then that can be replaced with a sine in the numerator. Or tangent can be changed into sine over cosine. Those are the types of substitutions that we can make. And then once we make those substitutions, a lot of times we're going to see that there's some cross-canceling that we can do. We've got the Pythagorean identities. So the sine squared plus cosine squared equals 1. And then the two partner Pythagorean identities that we get after dividing everything by sine squared or dividing everything by cosine squared. Those are handy when we have multiple terms that we need to combine into a single term. We'll see what that means in a few moments. Sometimes we're going to have to factor. We'll see an example where that's necessary for us. And then sometimes we need to add or subtract fractions, which requires common denominators. The bottom line is these just take experience and practice. And a lot of times it just feels like we have no idea where to go. So my recommendation is, at a minimum, just try something. And a lot of times that something is to just start changing things into sines and cosines and see if that leads anywhere. With more practice and more experience, we get better at these. But let's see how it goes as we get started here. So again, the idea is we want to turn this cosecant times tangent into a secant. We want to demonstrate that these two things are indeed equal to each other. And so one of the things that I had on the list there was to just change everything into sines and cosines and see what happens. And so I'm going to do that. So for cosecant of theta, I'm going to rewrite that as 1 over sine. And I'm going to be lazy here and not write down the theta every single time. We can see it's the same angle everywhere, so there's no reason for us to have to write it every single time. Again, similar to the parentheses around sine squared, we don't write those, and we instead write just the little squared after the sine. This is another example of how we can just kind of shortcut things a little bit. Of course, it's sine of theta, but we'll shortcut that. So cosecant is 1 over sine, and then tangent is sine over cosine. So the first is from our reciprocal identities, the second is from our quotient identities. And so now that I've rewritten these as sines and cosines, I can see that there's some reducing that I can do. I've got a sine in the bottom and a sine in the top, and so I can cancel those out. And so then I can see that I've got 1 over cosine, which is still left. And then, of course, from our reciprocal identities, 1 over cosine is equal to secant. And so here we have indeed shown that these two statements, cosecant times tangent, is indeed equal to secant. And so a lot of this is obvious. Once we set it up as those 1 over sine and sine over cosine, we can see very quickly where this is headed, but we have to remember that this is a proof. And so in all of these cases, the statement that's presented to us is indeed true. And so it's our job to verify that it's true. And so that means that there are going to be steps that we're going to have to show that we might otherwise skip if we were just solving an equation or something like that. So the next one is going to have much of the same sort of thing happening. I can see I've got cotangent times secant is supposed to end up equaling cosecant. So I'm going to use my quotient identities and reciprocal identities to work on this left-hand side. Again, the right-hand side, this has to stay as is. I'm trying to turn the left-hand side into the right-hand side. So cotangent of theta, that can be rewritten as cosine over sine. And then secant of theta, we just saw that a moment ago, is 1 over cosine. And so we've made these two substitutions. Now, once more, very similar to the previous question, we can see that the cosines in the top and bottom can cancel out. And so that leaves us with 1 over sine, which is indeed cosecant. And we can go with a little check, boom, if we want to feel a little bit sassy here. In the next two examples, we have a little bit more going on, certainly. In the first one, we've got this sine squared plus this sine times secant times tangent, and then plus this cosine squared equals secant squared. So this is an example of what I was talking about earlier, where we've got multiple terms. We've got sine squared plus this mess plus cosine squared, and somehow all of this just ends up having to be a secant squared. So that means we're going to have to use our Pythagorean identities eventually to eliminate these some of the multiple terms that we have on this side. So the first thing that I can see, in fact, are the sine squared and cosine squared. So I'm going to rearrange the deck chairs here a little bit. And so we've got sine squared plus cosine squared, and then plus I've got the sine times secant times tangent. And so the reason I've rewritten it this way is because this is the first spot where I'm going to be able to take advantage of one of our Pythagorean identities. Because if we recall from the original, sine squared plus cosine squared is equal to 1. So I'm going to take that and make it 1 plus, and now sine times secant times tangent. Now I need to deal with this sine times secant times tangent. So I'm going to do the same thing that we did on the previous two examples, is I'm going to resort to changing these to sines and cosines and see where that leads. So I still have this 1 plus, well, sine is already a sine, so I'm going to leave it like that, times 1 over cosine times sine over cosine. And so what I can see here is no cross-canceling of any type, but at least I have the same thing on the top and the same thing on the bottom. So I can rewrite this as 1 plus sine squared over cosine squared. And now I can work backwards on my quotient identities to change this sine squared over cosine squared into a tangent squared. If sine over cosine is tangent, then sine squared over cosine squared is tangent squared. And now once more, I can see that I need to use another Pythagorean identity because I've got two terms, the 1 and the tangent squared, being added together to equal that secant squared. And if we roll back to our Pythagorean identities, yes, the original was this sine squared plus cosine squared equals 1, but if we divided all of those things by cosine squared, we ended up with this other version of the Pythagorean identity, which was 1 plus tangent squared is indeed equal to secant squared. And so that's what we wanted, since that's what our goal here was, is to turn this mess on the left into secant squared. And so we've got it. We'll throw an exclamation point on that one. So before we move on to this next example, we should talk about the versatility of the Pythagorean identities. So sine squared plus cosine squared equals 1, for example. So we used that in this previous one after we rearranged the original statement, and we grouped that sine squared plus cosine squared together and replaced it with a 1. So likewise, I can rearrange this Pythagorean identity. So let's say, for example, I subtracted sine squared from both sides. Well, that means that I've got cosine squared equals 1 minus sine squared. So that means that's a substitution that is available for me. Whenever I see a 1 minus sine squared, I can replace that with a cosine squared. Or likewise, if I took, let's say, cosine squared away from both sides. So let's say I did that instead, subtracted cosine squared from both sides. So now I've got sine squared equals 1 minus cosine squared. So that's a substitution that I'm allowed to make. So any rearrangement of these Pythagorean identities is available to us for use in these examples. And so that's going to be really the first step that we're going to use on this next one. So we can see that we've got a mix of sines and cosines. We've got this fraction. We've got a couple subtraction pieces. And so in the first step, and let me just clear a little space here. In the first step on this one, in this numerator, I've got 1 minus sine squared. And so from right over here, I can see that I can replace that with a cosine squared. So that's going to be the first step that I'm going to take. The other thing I'll point out before we get started is you can notice I've got a different Greek letter representing my angle. That's the Greek letter phi. On the previous examples, it's been the Greek letter theta. In the worksheet that you'll be working on, it's x everywhere. It doesn't matter. As long as that's the same thing throughout the entire identity that we're trying to verify, then it doesn't make a difference. It's just a variable is all it is. So 1 minus sine squared, back to that. So I've got 1 minus sine squared is equal to cosine squared. So that's going to be the first substitution that I'm going to make. So now I have cosine squared over cosine squared minus sine squared. Now cosine squared divided by cosine squared equals 1. So I can divide that and make that 1 minus sine squared. And once more, I'm going to use the exact same identity that we just used. 1 minus sine squared can be replaced with cosine squared. And as we can see, we've got our equivalent statement there.